This is a lesson on applications of the second law of thermodynamics, heat engines and heat pumps, in the heat and thermodynamics unit. In a prior lesson, we had gone over the key concepts of the second law of thermodynamics. Applications allow the quantifications of the law to become apparent. The law is fairly simple. Heat will flow from the hot reservoir to the cold reservoir. The quantification of it comes from accounting for those heat flows. The heat in has to equal the work that the heat engine puts out plus whatever cold was left over and goes to the cold reservoir. The purpose of applications is to maximize or extract the work from the process in the natural direction. This simple equation allows us to keep track of all of those types of energies, and the applications center around the maximization of the work. Therefore, when you look at the quantification of the second law, you will see efficiency going on. Efficiency is defined as the fraction of the total energy that was extracted from the heat transfer process and directed towards work. So you will see I have a different diagram, but it is similar in concept, but overall it represents the same process. And what we're doing is we're keeping track of QH, the work, and QC. What we really want is to maximize the work out. And so when we look at efficiency, we're going to take the ratio of what we get out in terms of work over what was put in to begin with, what could have possibly gone towards work. Ideally, we'd like all of the QH to go to the work, but this is a natural process and this is what we observe in physics. There's a portion of heat that goes to the cold reservoir. Note that QH is the total possible, such that 100% efficiency occurs when W equals QH, such that this path is maximized and no heat is lost to QC down here. When I rearrange this equation, and remember we keep track of the relationship QH equals W plus QC, when I plug in what I know about W, if I solve this equation for W equals QH minus QC, I can plug that into what I know for work in the efficiency equation, and this relationship comes along too, and you may see this in textbooks, this equation here. This equation is true for all heat engines. The example I chose is pretty interesting about a power plant. An electrical power station transfers 2.5 times 10 to the 14th joules of heat energy to work with an efficiency of 40%. It dispels heat into a 20 kilometer squared adjacent lake with an average depth of 6 meters. Okay, so let's think about the power plant in terms of our heat engine here. Obviously, there's going to be a lake here, and the lake is capturing the cold heat that comes from the power plant. Fishermen like to use power plant lakes because they're a little bit warmer because of the heat. There's a lake here and it's catching the cold heat. There's some heat coming in, and that's what I see this 2.5 times 10 to the 14th number is. It says of heat energy to work. So up here QH is 2.5 times 10 to the 14th joules. I can see that. What it's saying is 40% of this goes to work, which means the other 60% goes to the cold energy. So the question asks, how much electrical energy did the power plant station output? So they want to know what is the work. How much work was put out? Well, I have the efficiency equation here, work, so I can solve this for work. Work equals the efficiency times QH. And I'm going to take a moment to acknowledge that I've been a little wishy-washy with the absolute value sign, and because I know all of these values have to be positive. Again, we're not working with directionality. Energy is a scalar. There is no coordinate system here. What we do know is that we have already accounted for direction of heat transfer. There's definitely QH coming in. There's definitely W and QC going out. And so when I arrange this equation, I know all of those values are positive. If there's some sort of negative going on in here, it is not a natural process. So I will be a little inconsistent with the absolute values because I already see all of these as positive values. So I wrote W equals the efficiency times QH. So I can write that in here. Efficiency is 0.4 and QH is 2.5 times 10 to the 14th joules. And when I multiply these two together, I get 1 times 10 to the 14th joules. And that is the amount of work that is output by this power plant. So that's part A. Part B says, assuming uniform heating, determine the rise in temperature of the water in the lake due to this process. Okay, so we have Q cold coming out here, and it's used to warm up the lake. And it says that the lake is water. Okay, so I know how to determine a change in temperature due to Q. What I'm going to remember is that Q equals MC delta T for any substance, and I'm working with water. I know that I can determine the mass of the water. They gave me the volume of the lake up here, essentially, right? Volume equals the area times the height of the lake, and so the area is 20 kilometers squared. I'm going to convert that to meters, so 1 kilometer is 1,000 meters, and then I need to square that quantity in order to get kilometers squared. Then I have to multiply by the height, which is 6 meters. Okay, so I have the volume. To figure the mass, I can take the volume and multiply by the density of water. I know the density of water is 1,000, and the volume is going to be given by this number. I'm not going to calculate it yet. I'm going to just let it sit here. So 1,000 times the volume. Now that I have that piece mapped out, I know that QC has to equal MC delta T. So I'm going to solve this for delta T equals QC over MC. Okay, so this is the cold heat. The cold heat is going to be the hot heat minus the work, which is 60% of the original amount. But what I'm going to do is take the total amount is 2.5 times 10 to the 14th joules. QC equals Q hot minus the work, which is 2.5 times 10 to the 14th minus 1 times 10 to the 14th. And so I get 1.5 times 10 to the 14th. So I'm going to put that in here, 1.5 times 10 to the 14th. That's Q cold over M. I'm going to put all of these terms in here that I have to find M. I'm going to take the density, which is 1,000. I'm going to multiply by the volume, which is 20 times 1,000 squared times 6. And then I still need to multiply by the specific heat of water. The specific heat of water, if you don't know that off the top of your head, is 4,186 joules per kilogram degrees Celsius or degree Kelvin. It doesn't matter because it's the same scale. So I'm going to put that over here, 4186. Okay, so when you run this through your calculator, this is a huge number on top, but look, we have 1,000 cubed and times 4,000. This is a really big number down there. And it turns out the temperature change of this lake in degrees Celsius is 0.2986. 0.3 degrees Celsius. If you are more familiar with Fahrenheit, that is 0.5475 degrees Fahrenheit. So a little bit higher than half a degree in Fahrenheit. So that's why that lake water gets warmer. It's not terribly warm. If you've experienced it, if you've swam in lake water near a nuclear plant, it is warmer, but it's not hot. And you can see why. It won't rise a lot. It would take a lot of energy to really make it like bath water temperature. So how do we maximize the energy out? Theoretically, all engines have a maximum efficiency achievable based on the temperatures of the hot and cold reservoirs. Just because of those temperatures, there's a limited amount of heat that can be transferred from one reservoir to the other. So let's remember with the second law that the cold heat is going to be less than the hot heat in amount. And also the temperature of the cold reservoir is going to be less than the temperature of the hot reservoir. Here's a summary of the efficiency. Again, this is for all heat engines. Carnot theorized that the efficiency of an ideal engine is limited to the temperature of the hot and cold reservoirs. It's formally stated no irreversible engine operating between two reservoirs at two temperatures can have no greater efficiency than a reversible engine operating between those two temperatures. So that's the formal definition, and it is sort of verbose. And on the next slide, I get into a little bit more formalization and understanding why this must be true. What comes out of this theory is that the efficiency, called the Carnot efficiency for an ideal heat engine, is 1 minus, and notice this comes from this relationship here. When you plug in what we know about work being related to QH and QC, we get this relationship. What Carnot said is that the heat cold over the heat hot, this ratio is limited by the temperature of the cold reservoir and the hot reservoir. When we use this relationship in this equation, we get the efficiency for the Carnot engine. And it depends only on the temperature of the hot and cold. The importance of this is really heavy hitting, and why Carnot really knocked it out of the park here is that the substance and mechanism are irrelevant. The type of heat and where the heat comes from doesn't matter. All that matters is the temperature of those two reservoirs. In this, it also established the thermodynamic temperature scale. Notice if we put 0 degrees Celsius in, on top, it's fine if it's the cold reservoir, but on the bottom, 0 down there, we can't have 0 down there. We get an undefined value, and that can't be true. So Lord Kelvin came along and established the thermodynamic temperature scale that says there is an absolute 0, and that's why absolute 0 also corresponds to 0 motion. The absolute coldest reservoir that you can have is 0 motion. And so that's absolute 0. The hot reservoir will always have a temperature hotter than that, and this ratio will never explode in bad ways mathematically. So that is the Carnot efficiency. Let's think a little bit more about the heat transfer that happens in a Carnot engine. Okay, so what we have over here is our model of the heat engine. We have heat coming in from the hot reservoir. It divides into work and into some cold heat into the cold reservoir. Carnot says that the efficiency is limited to T cold over T hot, the relationship of these two temperatures. Why is that? Well, what happens is the process that is brought up in the definition of a Carnot engine says it can have no greater efficiency than a reversible engine operating between those two temperatures. When I map this onto a PV diagram, I end up with two isotherms. Notice that we start at point A. There's an isotherm, an adiabatic process, another isotherm, and an adiabatic process. What you know about the area under the curve here is that we want to maximize it. The shaded area here is what is going to be the work. And we're going to maximize that area under the curve by choosing the process that maximizes this area under the curve in order to get work out. This is what we know about PV diagrams, is that they tell us the amount of work being done in a process simply by looking at the shaded region under the curves. So we see that it's maximized when it follows this process here. So in theory, it made sense, but when you looked at the technical definition, this diagram helps the technical definition come to life as to why this has to be true. Any other path would cause this area under the curve to be less than this maximum work done, and so that's how we get the maximum efficiency. Again, notice that because this process is independent of substance, we obtain a temperature scale that is independent of substance. And so that's important considering heat engines, that we can use any natural process that operates with a hot reservoir and cold reservoir, we can extract heat out of. Carnot says there's a limit to the maximum efficiency that we get out of that based on those two temperatures. Let's look at an example of Carnot's ideal engine, which I've called suspicious machine. It says, what is the efficiency of a machine that 25 kilojoules of heat transfer at 327 degrees Celsius, which results in heat transfer to the environment at 27 degrees Celsius? What is the efficiency of a machine that 25 kilojoules of heat transfer at What is the efficiency of a machine that 25 kilojoules of heat transfer at 327 degrees Celsius, which results in heat transfer to the environment at 27 degrees Celsius and does 12 kilojoules of work? Okay, so I put the equations over here, and I put a diagram here to help us conceptualize what's going on. So it says T hot is 327, so I'm going to put that up here, and I'm going to add on 273.15 to get it to Kelvin. So this is 600 Kelvin. I'm going to put it in Kelvin because I know that I was just talking about the temperature scale having to be in Kelvin because of absolute zero. I'm going to put 27 degrees down here, Celsius plus 273.15, and this turns out to be 300 Kelvin. So those are TH and TC. They've also given me values for the heat in is 25 kilojoules, and the heat out is unknown, but we know the work is 12 kilojoules. Notice that this diagram is a very useful diagram when taking information from this problem and arranging it. You may draw a heat engine every time you do a heat engine problem, and I highly suggest you do that as a tool to keep all this information organized well. What is the efficiency of the machine? Well, efficiency of the machine isn't hard to find. It's work over heat H, which I can even do up here. 12 kilojoules divided by 25 kilojoules, well, that's 0.48 or 48%, which is actually a pretty high efficiency for a heat engine. So that's why I say it's a suspicious machine, which is why Carnot said that the heat is limited by the temperature. So let's see what the Carnot efficiency is and compare it to the actual efficiency and see if it's within reality. I'll go ahead and plug in my numbers. 1 minus TC, which is 300, divided by TH, 600. 1 minus 300 over 600. 1 minus a half, which is a half. So 50% efficiency. So when I compare the Carnot efficiency to the efficiency that it says that it's getting, I see that this is a realistic situation. If this efficiency was larger than the Carnot efficiency, that's not a possible process. The spontaneous process is limited to the temperatures of the hot and cold reservoirs, and in this situation is limited to 50%. I wanted to have a quick chat about heat pumps. Heat pumps are basically a heat engine run in reverse, and you can see the diagram here, which I have borrowed from OpenStack's College Physics, has the heat engine running in the reverse process. Notice that heat going into the hot reservoir, and there's heat coming out of the cold reservoir. So this is definitely in reverse. This requires work, and notice work is being added in order to facilitate this process being done. When we look at this sort of engine, the heat output is what we're interested in. We care how much heat comes out of it. A situation where we want to get heat into another area. We're taking heat from a cold reservoir and putting it into another area. This may be a heat pump that lives in your house that just pumps hot air into your room. So we're taking some sort of heat and pumping it into a room and using a cold reservoir and using some sort of work. So to evaluate how well this heat pump is transferring energy, we use a coefficient of performance. And so we have a ratio of what we want to get out, which is now the heat into the hot reservoir, over the amount of work getting put in. And you will see that this will always be greater than 1. The work coming in is a portion of the heat being generated. Because it takes work in order to facilitate this happening, the less work that it requires, the better. The less work we have to do in order to draw cold heat from the cold reservoir in order to make hot heat, the better. The PV diagram shows us the direction of this process, and notice it's the reverse from the prior slide. We have cold heat coming in. There's some work here that goes into having Q hot come out. Refrigerators are essentially heat pump, but instead of focusing on the work being put in the hot heat being put into the hot reservoir, we focus on the cold heat coming from the cold reservoir. We want to maximize that value. So in the coefficient of performance, you see the cold heat on top over the work, and we want to maximize the amount of cold heat being pulled into the Q heat for the amount of work we put into facilitating that process to happen. Again, you can see it's the reverse process of the heat engine. I picked the ideal refrigerator for us to work on as an example for heat pumps and refrigerators. Suppose you want to operate an ideal refrigerator with a cold temperature of negative 10 degrees Celsius, and you would like it to have a coefficient of performance of 7. What is the hot reservoir temperature for such a refrigerator? So if you want negative 10 degrees in your refrigerator, what must be the temperature of the hot reservoir for the most efficient refrigerator? So that's what we're looking at. We have a cold temperature, and we have an efficiency, and we have a bunch of equations. So let's follow our nose a little bit here with the information we're given and see where it takes us to get to T hot. T hot, I know, is related to T cold in the ideal Carnot engine. In the ideal situation, T cold over T hot is equivalent to Q cold over Q hot. And I know those values are in the equations over here for the coefficient of performance for a refrigerator. And for just, this is the basic quantification of the second law, relationship between those energies in the heat engine. I'm going to solve this equation for W. So I get W equals QC over this coefficient of a performance, and I'm going to plug it into this equation here. So I get QH equals QC over the coefficient of performance plus QC. I'm going to take that and plug it in over in this equation here. I have QC over QH, which I have an expression for QH, QC over COP plus the QC, and I know that equals TC over TH. You may see that I'm a couple of steps of algebra away from solving for TH on one side. There's a QC in all of these terms. This will cancel to a 1, that's a 1, and that's a 1. There's a lot of 1s going on in there. And then when I solve for TH, I get TH equals TC times all of this stuff, 1 over COP plus 1, the coefficient of performance in here. And I have only 2 values. That was a nice little game of algebra that let me get the equation real quick. The TC is in Kelvin, so I'm going to add 273.15 there. 1 over 7 plus 1. When you run this through your calculator, TH equals 300.57 Kelvin, which is about 27 degrees Celsius or 81 degrees Fahrenheit.